Okay, so now that our best fit line equation shows this equation here, we concluded that to be y hat equals 0.03283 x hat plus 0.36041. And so here's the next thing we can actually do with this best fit line equation. And before I proceed on further, I actually have to admit that I used the slope and the y-intercept value that through the calculation r, and then m equals r over sy over sx, and b was y bar minus m x bar. So in the data here, I was using 0.84425, and I was using, so this calculation, this R here was done by using running the linrec command to get that, but I actually used these two formulas to obtain my slope and my y-intercept. And so in that way, here's the data here. Let's briefly look back into that. The same data we've been doing through the whole lecture. And so now that, so of course, in terms of the precision, then these values I calculated through the formulas are not as precise as those values being instantly pulled out from the calculator. But that's not really the main aim of this lecture here. So anyway, so here we already had the equation of the best fit line. So this time I'm going to purposely bring up this question right here. We want to find y hat 1. So unlike the earlier examples where I was saying just simply find y, and the person who giving the answer has to be the one in position that making the decisions to whether give a y hat or y. And I made an explanation with the difference between why we have to use y hat and why we have to use y. But here the question now is really intending to find y hat. And so, and notice that there's a subscript 1 right here. So now indicating that on our table, go ahead and look at the data again. So this value, the first data value, the first data pair, then the x value there is called x1. And so we have x1 equals 5. And in the first data pair, we already had y1 equals 0.45. And so this question here is asking for finding y hat 1, meaning we are going to find the predictions using that x value, x1 right here, from the first entry. So that means the intention now is pretty clear, and the instruction of the problem is pretty clear. So I am going to substitute my x1 value into the best fit line equation. And so what I have now is laying down the work, y hat 1 needs to come out as 0.03283 multiplied with 5 plus 0.36041. And so calculation shows that I have my y hat 1, my prediction corresponding to x equals 1 in the data. My prediction is 0.52456. So that is my prediction versus what we already had being the observed value. So once again, just want to one more time highlight the terminology here, but this is observed value, whereas this is a prediction or a predicted value. So in the next step, what I'm going to be doing, the y value, the observed value for y1 here we already had. I'm going to subtract the predicted value we just calculated through the equation. So here we're looking at 0.45 minus 0.52456, and then calculation here comes out being negative 0.07456. And when it comes to these, usually I use 5 decimals for a good precision. And so what is this? This is basically, this number right here came out as the difference between observed value and predicted values right here. So the predicted value is the value right on the line. It stays right on the line, and this is slightly, could be up, could be down. So this is the observed value, and so here we show a difference of being a negative difference. But once again, what to understand here is that this number we just finished calculating is the difference between observed value and predicted value. So in formal statistics term right here, then this value, the difference between predicted value and observed value, is referred to as the residual. It's just the difference between observed and prediction. It's being regarded as residuals. And residual here has a symbol. We use a symbol lowercase letter e here. And since now you can see that, think about what's happening, what's waiting ahead for us here, but this is the first pair of values. So I found the residual here is simply the residual for the first observed value y1. So we had a residual as being negative 0.07456, but we're going to have the later ones that corresponding to the other data pair right here. So here, correspondingly, I'm going to call this residual E1. So once again, residual is the name of this difference between observed and predicted value. But as symbolically, it's lowercase letter e, and I gave the subscript E1 here, the subscript 1 here, indicating that it's the first residuals in our data. And so here, let's continue, and one more time I'm going to repeat pretty much the exact same steps right here, but here we're going to find a y hat 2. And so now, after seeing the step-by-step example earlier, so now y hat 2 refers to, on my data, x2 is being 6 for the value, y2, the observed value there, correspondingly was 0.62. But now the intention here is that to use this x2 value and substitute into our previously found best fit line equation. And once again, I'm still staying with my equation version where I obtain the slope and the y-intercept from the formulas. And so the question here once again is looking for y hat 2. So what we're doing here now is that y hat 2 is found by substituting x2 values into the equation. So what I'm looking at here is 0.03283 times 6, that's substituted value for x, plus 0.36041. So now calculation turns out to be y hat 2 equals 0.55739. And so that is my y hat 2, and so here we can start speeding up the process a little bit. So the next thing I'm doing here for y hat 2 is I am going to consider the difference between y2, the observed value at data pair number 2, minus the predicted value y hat 2. And so the work here turns out my y2 being 0.62. My y hat 2 is 55739. The subtraction here happens in that order, and so what we're looking at here is the value positive 0.06261. And so once again, as far as what we call this is another residual. It's another residual again. And Yes, it's another lowercase e value, but it happens on entry number 2 on the data pair value 2, data pair 2, so it's E2. And so now at this point we have had about 2 residuals. I am going to create a third column in my data table right here. So here's my hand sketch data table that we have been working with since the beginning. And so the residuals, I'm going to start recording them. So these are residuals being recorded in the third column. So for the first pair value, x1 is here, y1 is here. So the residuals, I don't need to list. Notice, I don't need to list the prediction value. All I needed to list the residuals. So here I'm looking at negative 0.07456. That was our previous calculation. And just now we finished getting a positive 0.06261. And so there are more calculations waiting for us to come. But so far, after the 2 calculations, you can see that residuals, in a way how it is, it came out as a difference between observed and predicted values. So residuals could be negative or could be positive, and it happens all over. And so I'm going to spend a little time finish calculating out the other residuals that's still waiting for us here, and then I'm going to actually complete it all in my Microsoft Excel table. All right, so here is my well-prepared Microsoft Excel table that has, so here's the here's the X column that's listing out all the observed X values, and here's the Y column listing out all the observed Y values, and this third column now is for all the residuals. So our calculation came out with being negative 0.07456, and it was listed here, and this is my Y hat 2. I mean, my residual is E2, this is the residual E1, and so these are the rest of the other residuals that I finished calculating. Alright, so what are these residuals that we calculated, and what do they represent, and how useful can they be? And so let's say I'm going to, actually this time I'm going to use Desmos, a web-based graphing calculator for demonstrating the scatter plot of this data one more time. So here's my scatter points right here, and so I can once again display the points on the value, coordinates value on each of these points here. Remember, right from the beginning, we treat each pair of value as one coordinate point. So say when x value equals 5, we got a corresponding value being 0.45. So it's right about here. And so, so these are the scatter points. So now the best fit line equation that I already calculated, my equation here is the 0.03283 x hat plus 0.36041. And I remind everybody that I used these values that I obtained through the formula. And so the equation of that best fit line is here. And so it gives this line right here with that slope and y-intercept calculated. So once again, all of these scatter points are bouncing up and down. So some points are above the line, some of the points are below the line. So now let's look at our first value here. So the real observed value, the y1 was 0.45, but y hat 1 is indeed, when x equals 5, then y hat 1 would need to be the point that's on the line right here. That's on the line. And so the residual is negative 0.07, etc., was to represent that difference. And remember, it was negative, so indicating that the difference there, 0.07 something, was the actual difference, but being negative, it was indicating that our actual point, scatter point, was below the prediction line. It was below the regression line, the best fit line right here. So likewise, y hat 2 that we calculated had value 0.55739, and the residuals there was a positive 0.0 6261, so it's a positive residual, and so that means our distance here was a positive distance, and here it goes. The point was staying above the best fit line, and it's making a positive distance from where it is to where the line is. And so in that way, for the rest of the other points right here, every point makes some difference. So some points stays below some points stay below the regression line, some other points stays above the regression line. And it could be that for our human eyes viewing the data, sometimes it's even such a challenge matter to find out whether a point like this or a point like that being on the line or off the line. But the calculation of residuals can start telling the truth right here. So based on our calculation, and let's say this is 1, 2, 3, 4, 5. This is residuals number 5 right here, E5. So if looking through the graph, and it's not clear whether our point is on the line or off the line right here, above or below. Maybe here we can still see it. But E5 was this value right here, and it was negative, obviously, and so the line was indicating that value, that small line right there, but still little red right there being pointing down. And then for the other values, for the other points, so now I put up, and the residual is extremely beneficial when you're looking at something like this, where even if I zoom it in or I zoom it out, we still gonna see a small distance. It's gonna still be hard to find out whether the point is on the line or off the line right here. But so that's the usefulness of tracking down and calculating down all these residuals. All right, and then after calculating each individual residuals, and also having some understanding of how the residuals are relating to the scatter plot, and having the best fit line put together. And so we can now also calculate the standard deviation of residuals. So to start out with that, the standard deviation of residuals is indeed, it's just simply the average of all residuals. And so one more time, look back into my graph here, my scatter plot here. So these are all the different residuals. Some residuals negative, some other residuals being positive. So we want to average all of these residuals, these little distances between the actual observed value and the line, the best fit line right here. And so, but it's not simply just the mean value formula, but here when it comes to getting the average of all residuals, and formally speaking, now we call it, it's a standard deviation of residuals. But what we're looking for here, we're actually using a formula. Our E1 residual, the first residuals, I'm going to square that. So keep in mind that the square here is after considering even the sign of your E1, because each one of your residual could be positive or negative sign. So make sure you put your residuals in parentheses, then square when you're doing real calculation. Plus, and here we have E2 in parentheses, square, and so we square all residuals, E3 square, and keep repeating and adding all of the squares of residuals until we reach to the last one. So E sub n, which is your last, E, your last residuals. And so if there are n residuals in your data, we actually divide by n minus 2. And then we will be taking a square root right here. Okay. And so that is the formula for calculating the standard deviation of residuals. And the residual standard deviation is famously known for using a lowercase s, but this standard deviation is a little special standard deviation. So we introduce a little subscript e right here. E stands for the residuals, those symbols for residuals. So here we're finding the standard deviations of all the little residuals. And so the last thing to wrap up with our data that we've been studying since the beginning of correlation and linear regression here, the same data here, let's have a look at that one more time, and then we're gonna give a calculation using the formula. And we're gonna be giving a calculation for for calculating the standard deviation of all these residuals. Well, gladly that we have only 7 pairs of values. So, and there hasn't really been any technology method, any technological solution that handle the calculation here faster than using the formula. So, for viewers out there and former students in my class, feel free to look for a good technology to handle this. But for years teaching this, I've been always, when it comes to this, I've always been using a small data set so that it saves time for my student when they have to use the formula. And I never found any good way of using the technology for this. So now right here in your data, SE, standard deviation of residuals equals, so allow me once again to write each one of these with order of operation involved in here. So my first residuals was being a negative 0.07456. So make sure that we square including the sign of your residuals. So that means we put parentheses there. And once you got that square, then we move on to the next one. The next residuals here is being 0.06261. Squaring that, and then the next one here is going to be negative in parentheses 0.09305 square, and I'm running out of space very soon here, so I'm going to leave dots indicating that we're repeating doing this until our last residual is on the list. It's negative 0.00286 square. And then so now, even though I'm leaving the dots here, but if we really were doing all that calculation, I am expecting to have 7 squares of residuals being added up, and then we are going to divide by, so n in our data, n equals 7 pairs of data as a reminder. So here we're looking at divide by 7 minus 2. So we need to make sure you add up all the squares of residuals first. Then we divide by n minus 2. And the last step here is to be taking the overall square root here. And so now I'm ready for my final calculation. So SE equals, all right, so calculation comes out equals, SE equals 0.08368. 5 decimal, that should be good. But this is now what? This is telling us and once again back onto my graphing device right here. But this average that we're looking at is, think about so the reason we square each of the residuals is because we just simply look into the positive differences, even though some of these points are below, but we purposely look at just the positive distance. So the distance, the average of all these little distances from the beginning to the end. So we got all of the distances. So that average there, 0.08368, is going to be the average of all these little distances from scatter point to the body of the best fit line right there.